Welcome to the Beckhoff webinar with the topic Evaluation of LVDTs and inductive Hall bridges in the Beckhoff system. My name is Irina Koring. I'm working in the product management I/O and I'm responsible for the EL5072, our terminal for direct evaluation of LVDTs and inductive Hall bridges. Let's start with some general topics. If you have any questions during the webinar, please feel free just to put them into the question window. I will answer those questions directly after the webinar or afterwards per email. The agenda for today, I want to start with some typical applications for the use of the inductive sensors, go on with the main technical data of the EL5072, and show how you can configure this terminal in reference to your sensor. In the last step, I want to give some application notes. LVDT means linear variable differential transformer. So it's a transformer with some special design to be used for displacement, length, or position measurement tasks. LVDTs are passive devices, so they don't have any electronics included, and therefore they are often evaluated for their lack of electronics, which make them not sensitive for external influences. Furthermore, the measuring range presents often only some few millimeters with a high accuracy in the micrometer range. The advantages are obvious. It's very precise and a cheap solution with no mechanical wear. Therefore, there's also a wide field of application for such a kind of sensors. So starting with the measurement of workpiece geometries, thickness, length, or height difference measurements, radial or axial runout can be measured. Here, not only with one sensor, but with many cases also with two sensors or even more, just to check the height difference measurement or measurement of the corners. But also in the field of press fit and joining processes, LVDTs are used. Moreover, if there's a demand to check the dimensional accuracy of finished workpieces in the line quality control or at the end of line tests. Last but not least, also in the field of structural monitoring, for example, for bridges. Here, long-term measurements are carried out to determine deformation of materials. Here you can see a fair demo. It's a setup for workpiece measurement. In this case, the workpiece is an stairs mover. We have really a compact and small design, so it's consisting just of one linear axis controlled with a servo motor and only few I/O components. Embedded PC of the CX5120 series, the EL7201 to control the servo motor, and the EL5072 to connect a 4-wire LVDT for the direct measurement of the LVDT. The setup reflects the Beckhoff idea very well. Everything from one source and in one system. The motor for the axis adjustment, the control of the motor via the corresponding terminal, and the measurement of the workpiece via the EL5072. Everything is connected directly to the compact embedded PC. The parameterization and the evaluation of all components is done in the same software. In our case, it's a TwinCAT. Additionally, also the visualization and operation of the measuring equipment tasks can be done with the touch panel at the HMI. Also, everything is integrated into TwinCAT. Therefore, Beckhoff enables the integration of the robust and secure position measurement technology directly into the control system. What are the main key points of the EL5072? At least it's a two-channel solution and you can connect and evaluate directly two inductive sensors. The EL5072 supports full bridges in LVDT design, but also inductive Hall bridges. Due to different connection points and input impedances, you can connect mostly all common sensors in the market. Therefore, you are really flexible in your design and can use the right sensor for your application. Furthermore, the advantage is that no additional converters or transducers are necessary for the use of the LVDT sensors anymore. These black boxes are always expensive and have additionally negative influences on the accuracy due to the multiple signal conversion. In addition, direct integration and evaluation of the signal also offers a better diagnosis and simplifies the handling of the data. terminal can be directly parameterized via EtherCAT and no additional configuration software is required. The signals are read out and forward directly via EtherCAT to the controller. We can have a dynamic signal with cycle times in the range of 100 microseconds. The measurement process can be accelerated and thus also save time and costs. Last but not least, also various diagnostics are implemented and also allow faster troubleshooting. Let's have a look on the technical data of the EL5072. This terminal provides one excitation source in the range of voltages between 0.5 up to 7 volt ms and frequencies. It's a sine between 1 kHz up to 20 kHz with a maximum current of 50 milliamps. At least we have one source for both channels, therefore the synchronization of these two channels is really easy because the sampling is done with the same sampling time. The signal can be measured back with a range of 7 volt ms. Furthermore, we are using internally 24-bit sigma delta ADC, and the calculated position value is presented as a 32-bit value. It's an output in nanometers. Here the functions are presented. Even if we have an analog interface internally, not the analog row values outputted for the process data, inside the terminal we are doing some pre-processing and provided already a calculated position value. So you as a customer don't worry about any calculation specifications depending on the connection technology. The terminal already takes care of all of this. But of course, you still have some correction possibilities for the signal. It could be some filtering of the signal, but also the adjustment, just a simple one via offset and gain parameters, but also a lookup table with up to 20 entries is implemented. If you connected, for example, the power supply in a reverse polarity or just mounted the probe upside down, you can use the direction inversion bit just to reverse the connection. So you can so a plus position can become a minus one. Furthermore, the terminal offers one digital 24 volt input per channel. This can be, for example, used to set a position to be used as a Tara, or even if you're working with 2 or 3 sensors and you don't want to measure the relative but the absolute values, you can use the set position to set the position as an offset to get the absolute values. Furthermore, different diagnostics options are available. Beside the EtherCAT communication diagnostics, also some product diagnostics is available. For example, if you have 2 probes and one of them draws too much current, so you will get a short circuit on the excitation source, it can be displayed. Also on the measuring side, we have some error detections. For example, if the input signal level is too high, this could be if the parameters were set in a wrong way or if there's some cabling error, it's also displayed. Diagnostic data is displayed in 2 ways. On the one hand, via an LED, so the installer operator can directly see the error, but for sure you also get this information reported with the software. In the next slides, I want to show you how you can parameterize the EL5072 correctly to your sensor. Here we need to focus mainly on 6 parameters, so connection type, sensor impedance, excitation frequency, excitation voltage, sensitivity, and overall sensor range. If all the parameters are set in the correct way, the EL5072 will close all internal bridges by itself, do some corresponding connections, determine the correct amplification factors, and use the required calculation method. So at least the output value becomes directly a position value measured in nanometers. Let's have a look on the parameters one by one. I want to start with the connection type. The most common technology of the LVDT is the 4-wire connection. 2 wires for excitation source and 2 wires for the signal voltage. The voltage between the 2 signals is measured, and we have a differential measurement method. So the value is internally scaled and calculated to be outputted as position. The measured output voltage is mainly subjected to the dependencies of a nonlinearity of the individual secondary coils, but also fluctuations of the integrated supply, for example, caused by some cable lengths. Furthermore, some sensors offer an additional line, it's so-called center tap. This corresponds to a 5-wire connection. The voltage between the signal line and the center tap is measured and put into relation. So we have here some gravimetric measurement. This measurement method evaluation offers some advantages and increase also the accuracy. This can be achieved because of the systematic compensation of disturbing influences, for example, some temperature drifts, deviation in the excitation signal source, but also different complex factors of the secondary side, and also common more disturbances in the signal can be compensated. With this measurement method, the voltage that is measured is independent of the excitation voltage, so temperature dependencies of this source are not relevant. There are also some sensors with 4 wires on the secondary side. In this case, we are recommending to connect these wires, also 2 of these wires of the coils as close as possible to the probe to realize a center tap and to enable a 5-wire measurement. 6-wire technology also offers the possibility to measure the excitation voltage in parallel with a signal with the sense lines without current and with high impedance. So the elimination of line-related errors is realized here. So we have also gravimetric measurement that is used, and the signal voltage and the excitation voltage are put into the relation, and also better accuracy can be realized. The connections of inductive half bridges, mostly the 3-wire technology is used. Here, the excitation voltage is fed in from the outside and the signal voltage is measured in between. We can also realize a gravimetric measurement by set the excitation voltage and the measured voltage into the ratio. By using additional sense line, the excitation voltage can be once more measured currentless with a high impedance. So same procedure like for the full bridge LVDTs measurement. Also here, line conditioned errors are avoided and we have a more accurate measurement. Let's have now look on the different sensor impedances. For the full bridges LVDT probes, the high impedance input is mainly the rule. And also the so-called MAPOS compatible probes can be connected with the high impedance use. Furthermore, there's also a possibility to choose a tether impedance. This is mostly used if you have the 3 or 5-wire half bridges. The MA impedance can be used always if you have a MA compatible probe. Here, just a short hint from my side. At least it's a connection over 5 wires, but you have only 4 signal lines, so 2 for excitation voltage and 2 for the signals. The 5th line is so-called virtual ground. Therefore, you need to choose on the connection type side the 4-wire LVDT. Now we can check the excitation frequency and the excitation voltage parameters. The terminal has an excitation source that can be set in a wide range of voltages between 0.5 up to 7 VMS, and also a wide range of frequencies between 1 kHz up to 20 kHz with a maximal current of 50 milliamps. If you will not find the desired voltage or frequency in the available lookup table entries, it is recommended to select the closest value, so if possible. We have made the experience that thereby a slight deviation in the measurement range occur. This can be corrected by user adjustment. The settings which are made in the CU parameters for first channel are also automatically applied to the second channel. One small hint from my side. The source is automatically switched off in the delivery state and must be switched on separately. The main idea behind this is that you will not by accident fit in the probe with a wrong voltage or to high frequencies. Yes, you will see that the source is off because the UP LED is flashing. If you will activate the sources, the UP LED will be automatically on. Now we can look on the last parameters, the sensitivity and the overall sensor range. The sensitivity indicates the ratio of the output voltage to the supply voltage and to the traveled measurement distance. This is the main conversion factor for the terminal to calculate the position value out of the measurement signal voltages. In the main cases, the sensitivity is valid for the calibrated range of the probe. So outside this measuring range, linearity errors can be occurred. The calibrated measurement range is usually smaller than the total travel way of the probe. The measuring ranges, the probe has the highest linearity and therefore also the highest accuracy, while inside the mechanical travel it's determined by the mechanical setup. The specification of the maximum travel distance is needed internally to determine the maximum voltage that can be measured back. If you will put a too low value here, some errors can be occurred because the measured voltage is higher and therefore it will be internally lead to an amplitude error. If you now have set all parameters correctly, you will receive your position value via the process data. This one will change the function of the probe movement. Now, of course, the question arises, what is the accuracy of the position value? To be honest, it's really difficult for us to make a general statement about the accuracy of the terminal. Our first experience show that we have here an accuracy range of smaller than 1% of the measurement deviations. What we can provide is an accuracy of our internal voltage measurement. But however, it's not really helpful for you as a customer, since this point is only one of many in the entire measurement chain. As just showed, the terminal offers a variety of connection options, and depending on these, internal measurement factors and evaluations algorithms are formed. So it would be not only one value that we can need to be specified, but many different values depending on the selected parameters. In addition, there's still always an interaction between the electronics and also the sensor. Therefore, we have created two possibilities to do a user adjustment. On the one hand, it's our offset and user gain parameters, and on the other hand, it's a looked up table with up to 20 entries. Let's have a look on a simple adjustment that can be carried out via the offset and user gain. The requirements for user adjustment are some comparison or reference values. Furthermore, for some half bridges, also so-called calibration probes are available from the manufacturer. This one are fixed in temperature stable resistance, and they reflect a certain position, for example, the 0 one or some calibration measurement ranges. Furthermore, of course, also stable environment conditions, such a temperature must be observed. The procedure for such an adjustment can be as follows. In the first stage, you can carry it out as zero offset adjustment. So, for example, you will move to the mechanical reference 0 and look on the output value of the terminal. Then you can write this value inside the offset register. In the next step, you can travel to the maximum positive measurement range and also check here the output values. Now you can implement the gain, so you will just set the ratio of the two values, so of the measurement and the target value, and put this one into the gain register. Then you can do a cross-check while traveling to the maximum negative measurement range. Probably you will need to do some readjustment to achieve a symmetrical behavior. Once more, some hints from my side. To automate and simplify the user adjustment, you can use the digital input. This offers you the possibility to store the measurement value at a fixed time. In our wording, it's so-called latching the value. So for example, you can travel to your mechanical zero, latch the measurement value by using the digital input, then it will be written in a separate register. You can read out this register and just write automatically this one to the COE data. You can do the same with the gain adjustment. Furthermore, you can just protect your data via some user password. So this data is separately then protected against overwriting. The protection applies on the COE write access by the user or the PLC or startup entries in a single or complete access, but also by overwriting of the setting objects just by activate restore default parameters. Finally, some application notes from my side. So after setting all the parameters inside the EL5072 correctly, including the excitation frequency and the excitation voltage, please switch on the excitation source separately, because in the default state the source is off. To achieve an optimal adjustment of your electronics and the inductive probe, and to achieve a better accuracy, please use the user adjustment and protect your data via password. The main cases, the errors occur because of the different cable lengths. If we are talking about cables, please consider that for medium cable lengths, shielded signal lines are required. If we are talking about longer cables, so if you're using cables more than 20 meters long, please use separate shielded cables for signal and excitation. Don't put both lines in the same shield. And last but not least, please also observe the warm-up times for the inductive sensors. This time can be up to 10 minutes before you will receive a good and accurate positional value. Now I'm finished with my presentation, and if you have any questions, please feel free to put them into the question window. I will now try to answer them, or I will answer them afterwards via email. Thank you for your attention.